April 6, 1945, off Okinawa, Japan. 1340 hours. Colonel Takeo Yamashita, 42, Japanese Army artillery commander, watched from cave overlooking East China Sea. 15 kamikaze aircraft diving toward American fleet. 0 fighters loaded with 250-kilogram bombs. Young pilots on one-way missions. Yamashita's binoculars tracked first 0 beginning terminal dive toward destroyer. Then the American ship's 5-inch guns opened fire. Not aimed fire. Barrage fire. Shells exploding in mid-air, creating walls of shrapnel between ship and aircraft. No direct hits needed. Shells detonating automatically when aircraft came within lethal radius. Yamashita watched all 15 kamikazes. 11 were destroyed before reaching ships, torn apart by shells that exploded near them. Not hit by them, near them. Traditional artillery shells detonated on contact or at preset time. These American shells seemed to sense aircraft, exploded at perfect moment. Created kill zones in 3 dimensions. Yamashita had studied artillery for 20 years. Commanded batteries in China, Philippines, Malaya. He understood ballistics, trajectories, fusing systems. What he was watching violated everything he knew about artillery. What Yamashita didn't know was that he was witnessing technology developed in complete secrecy since 1940. What he didn't know was that American shells contained miniature radar sets. What he didn't know was that this 5-pound device had made every Japanese defensive doctrine obsolete overnight. What happened next would convince Japanese high command that American technology had advanced beyond their capacity to counter. Not in 10 years. Immediately. By April 1945, Battle of Okinawa had revealed catastrophic vulnerability. Japanese doctrine relied on waves of kamikaze attacks overwhelming American defenses. Simple mathematics. If 100 aircraft attacked and 90 were destroyed, remaining 10 would sink 3 American ships. Acceptable exchange ratio. Traditional anti-aircraft doctrine required direct hits. 5-inch shell had to physically strike aircraft traveling at 300 miles per hour. Hit rate was approximately 3%. This meant to shoot down 90 attacking aircraft, ships needed to fire 3,000 shells. Time required, approximately 45 minutes. Kamikaze attack lasted 8 minutes. Japanese planners calculated Americans needed 15 seconds to aim, fire, reload anti-aircraft gun. In 8-minute attack window, each gun could fire maximum 32 rounds. Destroyer carried 4 5-inch guns, could fire 128 rounds total per attack. At 3% hit rate, each destroyer could shoot down 4 aircraft per wave, so Japanese sent waves of 15 aircraft. Against 4-ship destroyer division, mathematics favored attackers. 16 aircraft shot down, 14 got through, enough to cripple or sink all 4 destroyers. This doctrine worked until January 1943. Then something changed. American ships began shooting down aircraft at impossible rates. Not 3% hit rate, 70%. Japanese naval intelligence analyzed combat reports, found consistent pattern. American anti-aircraft effectiveness increased 7-fold beginning January 1943. Intelligence officers assumed Americans had improved radar fire control or deployed more guns per ship. Neither explanation fit the data. American ships weren't firing more shells. They weren't aiming better. They were using different shells, shells that exploded without hitting anything. On January 6, 1943, Japanese dive bomber attacked USS Helena near Guadalcanal. Helena's 5-inch battery fired 3 shells. All 3 exploded in proximity to aircraft without direct contact. Aircraft disintegrated from shrapnel. Fragments recovered showed American shells had burst approximately 50 feet from aircraft. Japanese Navy Technical Intelligence designated these proximity shells and assigned highest priority to understanding how they worked. The device that made this possible was called VT Fuze. VT stood for variable time, but this was deliberate misinformation. Real designation, proximity fuse. Most closely guarded secret of the war after atomic bomb. The fuse was marvel of miniaturization. 5 pounds, 6 inches long. 3 inches diameter, contained vacuum tube transmitter, receiver, battery, detonator circuit. The entire assembly had to survive being fired from gun at 20,000 Gs acceleration. Had to function at temperatures from 40 to +120 Fahrenheit. Had to operate after spinning at 28,000 revolutions per minute. Had to cost under $18 to manufacture. No radio device in 1940 could withstand these conditions. Standard vacuum tubes shattered at 100 Gs. Batteries failed at 500 Gs. Transmitters stopped functioning above 5,000 RPM, so American engineers reinvented every component. Vacuum tubes, redesigned with reinforced glass envelopes and shock-mounted elements. Tested to 20,000 Gs. Survived 95% of firings. Batteries. Replaced conventional dry cells with wet cell activated by centrifugal force. When shell fired, spinning motion forced electrolyte solution against metal elements, generating electrical charge. Battery activated automatically on firing. No shelf life problems. Transmitter. Used radio frequency of 200 MHz. Transmitted continuously after leaving barrel. Reflected signal from metal target returned to receiver. When return signal indicated target within 70 feet, detonator circuit fired. The mathematics were devastating. Traditional contact fuse required hitting aircraft measuring 30 feet wingspan traveling at 300 knot. Target area, approximately 450 square feet. Probability of hit, 3%. Proximity fuse detonated when aircraft entered sphere of 70-foot radius. Lethal fragment area, approximately 15,000 square feet. Probability of kill, 85% when shell passed within 100 feet of target. This multiplied anti-aircraft effectiveness by factor of 28. Single ship that previously shot down 4 aircraft per attack now shot down 112 aircraft. Except Japanese never sent 112 aircraft against single ship. They sent 15, so single American destroyer with proximity-fused ammunition could destroy entire attack wave before any aircraft reached bombing range. Japanese captured unexploded proximity shells. Beginning February 1943, fragments recovered from shot-down aircraft contained fuse components. Japanese Navy technical staff examined them, recognized vacuum tubes, electronic circuits, battery components. Then Japanese engineers tried to replicate the technology. First problem, miniaturization. American proximity fuse contained components requiring precision manufacturing to tolerances of 0.0001 inch. Japanese radio manufacturers worked to tolerances of 0.01 inch, factor of 10 difference. Second problem, rugged vacuum tubes. Japanese industry produced excellent vacuum tubes for radios, radar, communications gear. But these tubes operated in stable environments, not 20,000 G accelerations. Japanese researchers tested captured American tubes, measured glass thickness, 0.020 inch, measured internal support structures. 16 independent shock mounts. Japanese standard tubes had glass thickness, 0.008 inch. Zero shock mounting. Third problem, manufacturing scale. To make proximity fuses combat effective, Americans needed to manufacture 50,000 per month minimum. This required automated assembly lines, precision measurement tools, statistical quality control, specialized workforce. Japanese industry in 1943 was building 5,000 radar sets per month using largely manual assembly methods. Japanese Navy Technical Intelligence concluded in August 1943. American proximity fuse represents technology we cannot replicate with current industrial capacity. Estimated time to develop equivalent device, 18 months minimum. Estimated time to manufacture at scale, additional 24 months. Total timeline, 42 months from present, by which time war outcome will be decided. Report recommended defensive doctrine assume all Japanese aircraft attacking American ships would face proximity-fused anti-aircraft fire. Expected survival rate, under 30%. Japanese military command rejected this assessment, called it defeatist, ordered continued kamikaze attacks. assured pilots that fighting spirit would overcome American technology. But the mathematics were inescapable. Development of proximity fuse began. August 1940. Meeting between National Defense Research Council and Navy Bureau of Ordnance. Captain Gilbert Hoover represented Navy. Dr. Merle Tuve represented NDRC. Hoover's request: "We need shells that explode when near aircraft without requiring direct hit. Can this be built?" Dr. Tuve's response: "Theoretically, yes. Practically, we don't know." British tried using photoelectric sensors. Failed because sensors couldn't handle gun acceleration. "We're thinking radio proximity sensor." Never been done. No guarantee it's possible. Navy authorized $2 million research budget. Assembled team at Applied Physics Laboratory, Johns Hopkins University. Section T. Project code name: VT Fuze. Security classification: top secret. Team size started at 50 researchers. Grew to 10,000 people by 1944 across 26 contractor facilities. Total project cost $1 billion. Second most expensive secret project after atomic bomb. First successful test, July 1941. Test shell fired at drone aircraft. Proximity fuse detonated at 60 feet range. Drone destroyed by shrapnel. Project team knew the device worked. Now they had to make it manufacturable. Manufacturing challenges were extraordinary. Each proximity fuse required 47 precision components. Assembly process had 127 individual steps. Quality control required testing every component to 20,000 Gs using specialized centrifuge. Final acceptance testing required firing random samples from production batches and measuring detonation accuracy. Johns Hopkins Applied Physics Laboratory developed automated assembly lines. First production run, August 1942. Output, 500 fuses per month. Failure rate, 15%. By December 1942, 5,000 fuses per month. Failure rate, 8%. By June 1943, 50,000 fuses per month. Failure rate, 4%. By January 1945, 400,000 fuses per month. Failure rate, under 2%. The Pacific Fleet received first combat-ready proximity fuses in November 1942. Initial allocation, 5,000 units. Distributed to cruisers and battleships only. Security restrictions prohibited use where unexploded shells might be recovered by Japanese. First combat use, January 5, 1943. USS Helena, cruiser under attack from Japanese bombers off Guadalcanal. Helena's 5-inch battery fired 3 proximity-fused shells. All 3 detonated near aircraft. 2 bombers destroyed. 3rd damaged and crashed, returning to base. Helena's action report, January 6. New ammunition demonstrated extraordinary effectiveness. 3 rounds fired. 2 confirmed kills. Recommend immediate widespread deployment. Admiral William Halsey, South Pacific Commander, received Helena's report. Immediately requested 50,000 additional proximity fuses. Navy Bureau of Ordnance responded, "Production insufficient. Maximum allocation, 10,000 fuse per month for Pacific Fleet." Halsey's response, documented in memo dated January 15, 1943. If new fuse performs as reported, air defense effectiveness increases by factor of 10. Request all anti-aircraft ammunition be equipped with proximity fuses at earliest possible date. By March 1943, proximity fuses were standard equipment on all American cruisers and battleships in Pacific. By June 1943, destroyers were receiving them. By January 1944, all American surface combatants fired proximity-fused anti-aircraft ammunition as primary defense. The results were measurable. In 1942, before proximity fuses, American ships fired average 2,800 5-inch shells per aircraft shot down. In 1943, with proximity fuses, average dropped to 400 shells per kill. In 1944, average was 180 shells per kill. This wasn't just about saving ammunition. It was about survival. Destroyer under kamikaze attack had approximately 45 seconds from detection to impact. Could fire maximum 20 shells in that window. Without proximity fuses, probability of shooting down attacker, 7%. With proximity fuses, 65%. The Battle of Okinawa proved the technology's decisive value. April through June 1945. Battle of Okinawa. Japanese launched 10 major kamikaze operations. Total sorties, 1,900 aircraft, all attacking American fleets supporting invasion. American anti-aircraft guns fired 1.2 million 5-inch shells. 90% were proximity fused. Results: 1,465 Japanese aircraft destroyed before reaching ships. 435 aircraft got through. Of these, 181 hit ships. 95 caused damage without hitting. Japanese lost 77% of attacking aircraft to anti-aircraft fire before reaching targets. Traditional anti-aircraft fire in 1942 destroyed 18% of attacking aircraft. Admiral Richmond Turner, Okinawa Amphibious Commander, wrote in after-action report, "Without proximity fuse, estimated we would have lost 25-30 ships to kamikaze attacks. Actual losses: 26 ships sunk, 164 damaged. With traditional anti-aircraft ammunition, estimate would have been 100 ships sunk, 400 damaged. Proximity fuse saved the fleet." Japanese captured several unexploded proximity shells during Okinawa campaign. Army technical intelligence disassembled them completely, photographed every component, measured every dimension, tested captured vacuum tubes, analyzed battery chemistry, reverse-engineered transmitter circuits. Final report, June 1945, concluded, "American proximity fuse represents precision manufacturing and miniaturization we cannot match. Device contains 47 separate components manufactured to tolerances of 0.001 inch. Mass production requires automated assembly equipment we do not possess. Development of equivalent device estimated 24 months. Tooling and production setup estimated additional 18 months. Total timeline, 42 months minimum. Current war situation indicates American invasion of home islands anticipated in 12 to 18 months. Proximity fuse technology cannot be matched before war conclusion. Recommend all defensive planning assume American forces will possess this technology. Japanese forces will not." The report was filed. Never distributed to field commanders. Kamikaze attacks continued. Pilots were still assured fighting spirit would overcome American technical advantage. But Japanese artillery officers like Colonel Yamashita knew different. They'd watched too many aircraft die in mid-air bursts. They'd seen walls of shrapnel where seconds before had been clear sky. They'd counted aircraft losses, 77%. This technology represented something larger than just better anti-aircraft defense. It represented industrial-scale precision manufacturing. The proximity fuse wasn't one invention. It was systems integration of multiple technologies: miniature vacuum tubes, shock-resistant batteries, radio transmitters, automated assembly, quality control, mass production. Japan had scientists who understood radio, engineers who understood electronics, researchers who understood radar principles. What Japan didn't have was an industrial system that could manufacture 400,000 precision devices per month with 2% failure rate. That system was American advantage. Not better scientists, not smarter engineers, better manufacturing. General Dwight Eisenhower, Supreme Allied Commander, wrote in memoir, "The proximity fuse proved critical in two theaters, against V-1 rockets over London, shooting down 79% of incoming targets, against German armor in Battle of Bulge, where proximity-fused artillery shells detonating overhead created casualty zones impossible to defend against. But most important impact was Pacific Theater, where it made kamikaze attacks survivable." He continued, "Germans captured proximity fuses, examined them, understood how they worked, couldn't manufacture them. Japanese did same result. Not because device was too secret, because American industrial methods were impossible to replicate in time frame that mattered. Post-war analysis calculated the strategic impact. Proximity fuse increased anti-aircraft effectiveness by factor of 4 in Pacific theater. This reduced ship losses to kamikaze attacks by estimated 65%. Without proximity fuses, estimated American casualties at Okinawa would have been 8,000 additional naval personnel killed, 40 additional ships sunk. Those saved ships supported invasion that ended war in August 1945. Delayed ship losses would have postponed invasion timeline by estimated 3 to 4 months. This would have resulted in additional 100,000 American casualties and extended Pacific War into 1946. Japanese military historians reached similar conclusion in 1953 analysis. American proximity fuse made sustained kamikaze operations unsustainable. Pilot loss rate of 77% exhausted trained aircrew within 8 weeks. Replacement pilots with minimal training achieved even lower hit rates. By July 1945, kamikaze doctrine was militarily ineffective, due primarily to proximity fuse. The device that accomplished this weighed 5 pounds, cost $18 to manufacture, required 127 assembly steps, operated for maximum 90 seconds from firing to detonation. It represented perfect fusion of scientific understanding and industrial capability, and it won the anti-aircraft war. Colonel Takeo Yamashita survived the war. Surrendered September 1945. Repatriated to Japan 1946. Became professor of ballistics at Tokyo Institute of Technology. Published memoir 1962. Chapter titled The Shells That Exploded in Empty Air. Quote from page 156. I watched 15 aircraft die in attack that lasted 4 minutes. They were destroyed by shells that never touched them, just came near them. After that day, I knew Japanese anti-aircraft doctrine was obsolete. We trained gunners to aim directly at aircraft. Americans trained gunners to aim near aircraft. Their shells did rest. We could see the technology. We could measure it. We understood the principle, but we could not build it. Not because we lacked knowledge, because we lacked factories that could manufacture 400,000 precision devices per month. That was American advantage, not better weapons, better factories. Interviewer: Did Japanese scientists try to develop similar device? Yamashita: They tried. Navy technical staff built prototype proximity fuse in October 1943. It worked in laboratory, but it required hand assembly of 47 components. Took 3 days to build one fuse. Americans built 400,000 per month. Our 30 prototypes were interesting. Their 400,000 per month won the war. Dr. Merle Tuve, who led proximity fuse development at Johns Hopkins, received Presidential Medal of Merit in 1946. Citation read, 4. Development of anti-aircraft fuse that increased fleet air defense. Effectiveness by factor of 4 and saved. Estimated 40 ships and 8,000 American lives. Tuve's acceptance speech, November 1946. Proximity fuse succeeded because 10,000 people solved 10,000 small problems. Not one genius invention. 10,000 adequate solutions to manufacturing challenges. That's American engineering, making breakthrough technology mass-producible. Last proximity fuse manufactured was produced in 1952 for Korean War use. Total production, 1942-1952, approximately 22 million units. Used in anti-aircraft defense, artillery shells, rockets, guided missiles. Technology evolved into modern proximity fuses used in current weapons. Systems Japanese technical intelligence reports were declassified in 1975. Found this assessment from August 1943. American proximity fuse represents not technological breakthrough, but industrial breakthrough. Device uses known scientific principles. Innovation is in manufacturing methods that allow mass production of precision electronics. This industrial capability cannot be matched by Japanese industry at current capacity. War outcome may be decided not by superior tactics or fighting spirit, but by superior manufacturing. Report was marked defeatist assessment and filed without distribution. Today, Proximity fuses are standard in anti-aircraft missiles, artillery shells, naval guns. Technology developed 1940-1943 remains fundamental to modern air defense. Original VT fuse is displayed at Smithsonian Air and Space Museum. Placard reads, "The 5-pound device that made the Pacific Fleet survivable." There's a larger lesson. Proximity fuse wasn't most advanced technology of World War II. Atomic bomb wasn't most complex. Radar fire control systems wasn't most expensive per unit. B-29 bomber was, but proximity fuse was technology that could be manufactured at scale, that changed battlefield outcomes. It was adequate device produced in decisive quantities. Japan scientists understood proximity fuse, reverse-engineered it completely, built working prototypes, but couldn't manufacture 400,000 per month. That was difference between understanding technology and possessing industrial capacity to deploy it. Understanding meant nothing without manufacturing. Manufacturing at scale won wars. The last kamikaze attack of World War II occurred August 15, 1945, Surrender Day. 5 aircraft attacked American destroyer off Tokyo Bay. All 5 shot down by proximity-fused anti-aircraft fire. None reached ship. Perfect ending to technology that made American saying true. You don't have to hit them. You just have to get close. Close enough was good enough. When you could build 400,000 shells per month that got close enough,